So, in the discussion of special topics towards deep learning, let us discuss autoencoders and denoising autoencoders. So, there are interesting applications towards this, and the ideas are pretty straightforward. So, let me begin with the motivation. Suppose I am given an object and I want different layers of a neural network to be able to hierarchically learn different features, right. I want to have a hierarchy of mappings, and I want to learn these different features within different layers. Somehow when I compactly get towards a representation, I am in a lower dimension sort of. So, I have encoded, I have sort of removed redundancy, and I am in a compact representation for my input vectors. So, that is my encoding, right. And then I would like to pull my vector from the encoded state all the way when I have to decode it, right. If I have to decode it, I have to come up with another mapping, a nonlinear mapping that can take the encoded state towards the decoded output. But it is a sort of a code in a sense, because I have a mapping from a higher dimensional space to a compact representation in a lower dimensional space. And in the process of this encode and map and decode, which can be realized as a composition of these two mappings, I can do optimization over all possible mappings which are a function of the parameters of my neural network, that I can decode with a good deal of fidelity according to a distortion metric, right. That is the basic idea. So, let us work through the details. The concept is very simple. So, if you have digested how optimization can be done within the context of L2 and possibly regularization, you can easily see how one can build autoencoders. Okay. So, put in a nutshell, this is a neural network. Autoencoder is a neural network for data encodings and to learn a representation of a data vector in a reduced dimension so as to ignore signal noise. So, what is the idea here? Like I described earlier, we have a sequence of layers from the input all the way to the output to learn local features through a hierarchy, and we do this because we learn local features all the way to features that are less local, right, to less local features, and in this process we eventually learn the object. And the decoding layers will decode the learned encoded information. Now, in the context of a qualitative discussion, what do we mean by learning less local features as we get towards the object, as we eventually learn the object? So, imagine I have to learn the image of a cat, right. Maybe my first features are possibly the ears of the cat, maybe the eyes, the structure, etc. That is my first step. The next detail would be the sort of whiskers on the cat, etc., right, or its or subtle details, subtle local features. So, in a way there is some sense of multi resolution that is happening as a process of learning the object, and this is how we do in practice, right. So, if I am observing an image of a scene, the first thing that comes to me is the dominant features in the image. So, imagine I have a nice portrait, I have the mountains and I see the river and something like this. So, the first thing that comes to me is it is a landscape, right. I get the features of the mountains, I get the features of the rivers, etc. That is my first level of approximation. Then possibly I can see other features such as the depth of the valley or the peaks or the number of peaks, etc., right. So, these are less local features. So, a neural network does this because I have a hierarchy of layers. I can learn selective features as I progress in the sequel. Okay. Now, what is the simplest structure? So, I have some input x, so I have all these layers that I indicate by this bold arrow, and I encode. So, let me use a different color here. Right, this is my encoded information, and from this I need to decode. So, let me call this x hat, though my diagram is exactly not of the same length between x and x hat. A subtle detail is output has the same number of nodes as the input, and typically we use feed forward networks such as the multi-layer perceptron to accomplish this task, but this is not a restriction. You can also have other configurations to realize these autoencoders. Okay. Let us see what this means in terms of a representation, right. Let phi of E and phi of D B nonlinear mappings. So E stands for encode and D stands for decode. Phi of E takes a point in the space script x to this space which is script f. So x belongs to Rd and that corresponds to our space script x, and this vector z belongs to Rk, and I denote this as the space script f, and typically k is less than d because this is how we need to construct. That is, I want a compact representation, compact coded representation, so that I can ignore the signal noise, right. Now you can think about phi d as a mapping from this space f to this space which is script x. Now I want to choose mappings phi e and phi subscript d, which should minimize the reconstruction error, and so x is where I start with, that is my data vector. Then I look at the compositions of the mappings. So again this composition has to be in the right order. So first I do f phi e, then I compose it with phi d in that order. This is the order of composition. That is acting on x, and this gives me my x hat, and I want to minimize this metric, norm squared metric, over all possible mappings phi e and phi d. So maybe I put star here indicating that is the mapping which is optimum that I need to choose. And if you were to be a little savvy, you would take this expectation here over all possible realizations of the data vector x belonging to the space script f script x. Okay. So you can have a hierarchy of layers in this case, but let us consider a single hidden layer, okay, for purposes of simplicity. Let us consider a single hidden layer. This is within the context of our multi-layer perceptrons. So my vector z, which is encoded information, can be given as sigma of wx or plus b, that is my mapping, right. You can put a transpose, or I leave it here like this. So that means it is there is a transpose, depends on, you can put a transpose if you want to, okay. And the sigma is this function that I want to choose, which can be my sigmoid, or it can be my rectified linear unit or ReLU, okay. The z here is the coded representation, and it is also called the latent representation. Now the reconstruction is pretty straightforward after having seen how the encoding works. We just have to go through the inverse map. So, my x hat is some sigma hat which is not necessarily like what I have for my sigma that I have in the encode path. It is some sigma hat of some w hat transposed z plus bias b hat, right, and we need to know note that these are nonlinear mappings. So, my loss function is, if I just consider the vectors x and x hat, I look at the Euclidean norm between x and x hat, and if I express this compactly, this is x minus. So, first I have to have the encode, which is I do the sigma of w x plus b, that is what I do first. Then one sigma w x plus b, then what I do is I do the w hat on top of this plus bias, okay, and then I do a sigma hat on top of this. This is a b hat here. Okay. So, we have this normed square for two vectors x and x hat. So, this is like my x hat, but if you are looking at the average loss, then you have to minimize this over all possible realizations of the data vectors x. So, one can also minimize the average loss computed by taking the expectation operation over this loss function. Okay, and this is this sort of completes what autoencoders does, what autoencoders do, right, and the idea is pretty simple. That means what we need, the idea is pretty simple. What we really require is a latent representation of the data vector, and that is done through a forward encode mapping to a point in a lower dimension, and then you follow the same steps to basically lift this point from the encoded space to the original space through a decoding mapping, and then you look at the loss between your input and the reconstructed data points, and then you want to minimize this loss. So, choose your encoding mappings or learn them in a way that you want to minimize this loss, right, and if you want to do this over all data vectors in some average sense, then you will have to bring in this expectation operation over the data vectors, and that is how you would build your autoencoders, right. The idea is pretty straightforward here, and having learned this we will now study denoising autoencoders.